All right, so welcome to another exciting episode of chemistry here at Spain Park High School. Today is a rainy Friday, March the 18th. Can you believe we're at March the 18th? We're in the fourth 9 weeks. You guys are almost juniors in high school, okay? All right? I should have worn the shirt that says, I thought getting old would take longer. But you guys, time's flying. So, again to review, what is a vapor? Go ahead.
It is a substance that is usually in a liquid or solid form that has turned to a gas.
Turns into a gas. Okay?
Yes.
So, I asked the question, 50 years from now we come back, will this bottle be evaporated? Okay? And before I started the video, we said no. Well, some of y'all said yes. But if it's sealed well, there's no place for the vapor to go. So the water does begin to evaporate, vaporize. Remember, the difference between evaporate and vaporize is just closed container versus open container. Evaporation is from an open container. So it vaporizes, okay? But eventually it gets so much up here that they start bumping into one another. And what do we call it when a gas turns back into a liquid? Condensation. So it begins condensing. So it's evaporating and condensing, and eventually they get to where this is saturated, it's full up here, and then no more. So for every one that evaporates, one condenses. So we have what's called equilibrium. The forward rate, the evaporation is equal to the condensation rate. So there's a set amount of vapor above the liquid. Well, what causes pressure? For who remembers from yesterday, what causes pressure? Okay, or the very, when you go back and look at your notes, pressure is caused by what? Flip your paper over. What does it say?
Collisions of gas particles with the container wall.
Collisions with the container wall. So more molecules means more collisions, correct? So based upon however many molecules are up here, you're going to have a certain pressure. And we call that pressure of the vapor above the liquid, we call that the vapor pressure. Okay? The pressure of the gas molecules above. And so it gets to be a set. At this temperature right now, the water's evaporating and condensing. There's a set amount of water molecules up here. And so it's got a certain vapor pressure. So the pressure exerted by a vapor above its liquid is called? Anyone? What goes in this blank right here?
Vapor pressure.
Vapor pressure.
Oh, hey, Josiah did show up.
Okay, so the vapor pressure. Now, if you have a high vapor pressure, if it's a high vapor pressure, what does that mean about the number of molecules above the liquid? Is there a lot of them or a few of them? If it's got a lot of pressure.
A lot.
A lot, right? Because more molecules means more collisions means more pressure. So if something has a high vapor pressure, that means it's got a bunch of molecules above, which means it's evaporating a lot. So what does that mean about the attractive forces if it evaporates a lot? Are they strong or are they weak? If it's evaporating quickly, they're breaking apart easily.
Weak.
They're weak attractive forces. Okay? So the vapor pressure is a measure of the attractive forces. Liquids that have high vapor pressures, that means high vapor pressures means lots of vapor molecules. Because pressure and molecules are related. I mean, more molecules, more gas, more collisions, more pressure. You just always have to remember pressures caused by collisions. More molecules, more collisions. So they have weak attractive forces. Low vapor pressures then have what? High or stronger. They're still not going to be strong, but they're going to be stronger attractive forces. Increasing the temperature. So if I increase the temperature, what's that going to do to how much evaporates? Speeds it up. So that means I have more vapor molecules, right? So what does that mean about the pressure?
It's going to increase.
It's going to increase. More vapor molecules always means higher vapor pressure. So it just makes sense, if you heat it up, it's going to evaporate faster, so you have more vapor, so you're going to have a higher vapor pressure. It increases the molecules, giving them enough energy to break the bonds. This causes the vapor pressure to increase. Okay? So vapor pressure is real important. So if we look at a graph of this, once again, this thing is called your book. It's got lots of pretty pictures in it. Okay? Lots of useful information.
Whoa, it's like there's not a massive stack on the desk.
So on page 332 of your book is this graph right here. This is the graph of 3 different substances' vapor pressures. Try and get rid of the glare. Okay? Now, what did we just say? The higher the vapor pressure, what does that mean about attractive forces?
Weaker.
The weaker. Okay? So notice that at 20 degrees, which substance has the highest vapor pressure? How would we read this? We'd go up, right? What's the vapor pressure of diethyl ether at 20 degrees?
Like, almost.
Probably almost 600, 580, somewhere in that range. I mean, you go up 20 degrees and you hang a left wherever it crosses the line. Okay? Whereas at 20 degrees, ethanol is way down here and water is even lower. So what can we say about the attractive forces of water compared to diethyl ether? Who's the stronger?
Water.
Water. Okay? The higher the vapor pressure, so this has got the weakest attractive forces. This has the strongest attractive forces. Now, why is water's normal boiling point 100 degrees?
Because it likes itself.
What's this dotted line?
Good question.
What's the dotted line on there?
The boiling point of water?
Okay, well the boiling point of water is 100 degrees, and that's when it crosses over that dotted line.
That's at the 760 mark, right?
That's at the 760, which is, that's the torr, which is how many atmospheres? 1. That's normal atmospheric pressure. Boiling is, by definition, occurs when the vapor pressure equals atmospheric pressure. Okay? Now, the way I envision this, here's your water, and you're heating it up. Okay, that's my fancy flame. Okay? So, the water molecules in here, you heat them up, you speed them up. They're starting to move. They're starting to evaporate more quickly. Okay? But in order for the bubble to form down here, and remember, what's in the bubble when water boils? I keep asking this over and over again.
Water vapor.
Water vapor. It's not breaking up into hydrogen and oxygen because those hydrogen bonds are way weaker than the covalent bond holding the hydrogen to the oxygen. Water molecule, steam is still water. So in order for this bubble to form, what will happen to the level of this water if a bubble forms down here? If a bubble forms, what's going to happen to the level of this water?
Decreases.
Is it going to go up or down? It's going to go up. It takes up more space. So it's going to push this up. Well, what's keeping this from coming up? Think yesterday.
Surface.
Surface.
The atmospheric pressure. So the atmosphere is pushing down on this, okay? And so the water molecules are trying to push apart to make steam, a vapor bubble down here, but the atmosphere is saying, no, it's not gonna happen. It's not until the water molecules can push out with the same force that the atmosphere is pushing down that water begins to boil. Okay, so the vapor pressure, the water has to be able to have the same pressure out as the atmosphere pushing down. Now we just said that increasing the temperature increases the vapor pressure. So you can see the vapor pressure increases as we increase the temperature. So most of the time we make water boil by putting it on the stove. We increase the temperature until finally the vapor pressure equals atmospheric pressure and it boils. But right now it's storming outside. We have a low pressure system coming through, okay? Somebody get your phone out and say, hey Siri, what is atmospheric pressure in Birmingham, Alabama?
What is atmospheric pressure in Alabama? 29.91.
Okay, 29.91 is probably falling down a little bit. What did we say in inches? It was 1 atmosphere. 29.92. So we're down below, a little bit below, and it's going to maybe keep dropping even more based upon where you are with this storm.
So
Usually a storm is low pressure.
So technically the sky is falling right now.
Technically there's less atmosphere above us right now, that's right. Okay? So that means that as a low pressure comes through, it lowers this down. What does that do to the boiling point?
It gets lowered.
It gets lower. So normally we increase the temperature, we put it on the stove and make it boil, but the boiling point changes every day based upon atmospheric pressure. But we can make water boil if we can lower the pressure enough. Have you ever heard that they have high altitude baking instructions, that things cook differently in the mountains than they do at sea level? Because is there as much air above us in the mountain?
No.
Atmospheric pressure is less, right? It's hard to breathe because there's not as much oxygen in the air. So there's high altitude baking instructions because water doesn't boil at 100 degrees Celsius. It boils somewhere between 90 and 95 degrees. So when you put your spaghetti noodles into the water, okay, when you put your spaghetti noodles into the water, they're only at 90 degrees, they're not at 100 degrees. So here's some water. You just saw me fill it up. I had to make a good seal. I'm going to bring this. This is a vacuum pump. This thing really sucks.
Actually.
Literally. Okay, so I'm going to hook this up to this. Okay? And when I turn this on, it's going to start sucking the air out of here. And when it sucks the air out of here, I'm lowering the atmospheric pressure inside of this. So now, the water is boiling. Did I heat the water up at all? Rather than heating it up like we do on the stove and bringing the vapor pressure up to atmospheric pressure, this time I brought the atmospheric pressure down to make the water boil. Now I had to cheat and use warm water, but it's right down here. Because the vacuum, if I had a good vacuum, I could bring it down and make it boil even at cold temperature, ice cold. So you can adjust the boiling point by adjusting the pressure. So what would happen? What would happen if I did this in reverse? What if instead of sucking the air out, I pushed more air in and made the pressure greater?
It wouldn't boil.
What would you have to do to the temperature to make it boil?
Increase.
You'd have to increase it even more. Have y'all ever heard of a pressure cooker?
Mm-hmm.
Okay, a pressure cooker has a pot that has a lid that seals. So when that steam water begins to vaporize, boil, turns into steam, the pressure increases on the inside, so it keeps the water from boiling. So now the water won't boil until 140, 150, 160 degrees Celsius. So what is that going to do to, the rate at which food cooks? If it's going to cook at 150 versus 100.
It's gonna go a lot slower.
At 150, it's going to go slower?
No, it's gonna cook faster, but it's gonna take longer to boil.
Well, it's going to take longer for the water to boil, but once you get it there, things cook way faster in a pressure cooker because the temperature is so much higher. Because we can adjust the boiling point. Just again, remember, when water boils, it boils at a constant temperature. Didn't we talk about that way back at the beginning? Can't remember. Seems like we may have. No.
What were we talking
That water boils at a constant temperature. Phase changes occur. And then we've done that in advanced. Okay, so let me do that. I need to do that. Well, let me finish this thought and then I'm going to come back to that thought. Okay, so what goes in these blanks?
15.
Boiling occurs when?
Vapor pressure. Oh, wait, I shouldn't be answering these.
Oh, you already filled them
I already have a
in?
building.
Okay, vapor pressure of a liquid is equal to, somebody else then? Atmospheric pressure. Okay, if a high pressure, what happens to the boiling point? If it's high pressure,
Lower.
it increases. At more pressure, the water's got to get hotter to make the bubble form. Okay, that's a pressure cooker. Remember, a pressure cooker is high pressure. It requires higher temperature. The boiling point of the liquid increases. Okay, while a low pressure, what does it cause the boiling point to? Obviously the opposite, decrease. So in the mountains, and this is a great word, I love this word, rarefied. That means the oxygen in the air is rare. It is farther spread apart. It's harder to breathe in the mountains because the pressure is lower, so it's rarefied. Okay, it's a good ACT word for you. Okay, so I'm doing ACT prep for you right now, even though you're supposed to be doing, oh, I shouldn't say that on video. As a result, if the atmospheric pressure is less in the mountains, what does that mean? Does it boil at a higher or lower temperature? At a lower temperature than here. Okay? Liquids can be made to boil by either increasing the temperature or by doing what to the pressure? Decreasing the pressure. Okay? Now, let's just list the four main principles here. Number one, substances, these aren't anything new, are composed of tiny particles. And what's the tiniest particle of an element? What's the smallest part of an element? An atom. What's the smallest part of a compound? A molecule. Atoms or molecules. So these are very tiny. Okay? Particles are in continuous, rapid, random motion. So everything's moving. What determines how fast they're moving?
The pressure.
No, not the pressure though. What did you say? Oh,
Temperature.
the temperature. Heat them up, speed them up, cool them down, slow them down. That's what I'm going to put here. I'm going to say heat them up, speed them up. Okay? Increased temperature equals faster movement. Now, when do they stop?
Absolute zero.
They stop, no motion, at absolute zero, which is 0 Kelvin, which is negative 273 degrees Celsius, which equal to negative 459.54 degrees Fahrenheit. Close the parenthesis. And then lastly, all collisions between gas molecules are elastic. What does that mean, you think? The collision is elastic.
Stretches.
Okay, that's what that's what we normally would think. Okay, but in physics, when you have an elastic collision, that simply means putting this in parentheses up beside it. No energy is lost. If I take no energy is lost in parentheses. So if I take a basketball and I drop it, does it bounce as high when it comes back up? Why not?
It loses some energy from hitting the ground.
From hitting the ground, friction, some of the energy is transferred into the noise. It loses some of its energy every time it hits the ground. Even going through the air, it's running into air molecules and it's losing some of its energy due to air resistance. That's an inelastic collision. But an elastic collision is like you're bringing two magnets together. They don't really ever touch and they just kind of repel each other. So you don't lose any frictional energy. So you're not losing energy like you are in a basketball when the gas molecules collide, because they don't really ever collide. They just get close and then repel. So the gas molecules inside that can are just constantly moving, but you're not losing the pressure. It's not like a bouncing ball that eventually comes to rest. Those molecules inside the can don't eventually just come to rest. They don't lose their energy. They're elastic collisions. Okay? So, this is what we call the kinetic molecular theory. Okay? Just understanding that kinetic energy is energy of motion. So, everything's made up of atoms or molecules. They're in continuous rapid motion. You heat them up, you speed them up, you cool them down, you slow them down. Once you get to zero, they've stopped. There is no limit to how fast you can make them go. Okay? And then all collisions are perfectly elastic. Okay, that's just a lot of this is common knowledge we've kind of talked about. Okay? So, I'm going to come back, and I'm probably going to wait until Monday to get into the heating curve stuff, but what we have are phase changes. So let's just define some terms here. So if I go solid to liquid, okay? If I go solid, well, let's just keep them together. And then liquid to solid. If I go solid to gas, and then if I go gas to solid, or I could go liquid to gas, and I can go gas to liquid. Am I forgetting anyone? I think that's it. Okay? Is there any other possible changes? I think I got them all. So what do we call a solid going to a liquid? The phase change. What do we? It's a simple word. Everybody knows it.
Melting.
Melting. And the reverse of that is called, I heard it, freezing. Okay, what about a solid? Well, let's just do the easy one down here. A liquid to a gas. Boiling or evaporation, vaporization is what we'll just call it. But we can put out here, it's also boiling. Okay, that's the actual phase change, we call it boiling. But what do we call it when the gas comes back to the liquid? Condensing or condensation. I'll I'll say condensing. Condensing. If you look inside right here, okay, all that water was boiling, turned into a vapor, but now it collected on the sides. This is all the condensation. It's condensation when you have a glass of iced tea and it gets wet all on the outside. You can't put your iced tea down on the wood table because the condensation will leave a water ring on the wood table. So you have a coaster, right? Yeah, like on the top of your cup right there. That's condensation. All right? So it's the opposite. Rain right now is the water vapor in the clouds condensing so much it's coming down. Okay? But what do we call it when a solid goes straight to a gas? If a solid goes straight to a gas.
Isn't that what dry ice is?
That's what dry ice is. What do we call it when it goes the solid dry ice goes straight to the gas, carbon dioxide? Begins with an S. No? I know you know the word.
It's somewhere.
Okay? Sublimation.
Oh, yeah, no.
Have y'all heard that term before?
I remember learning it when we were learning about phase changes, like at the beginning of the year.
Yeah.
Like in August.
Sublimation. And what's the reverse of that? It's what snow is.
Snow.
You may not have heard of this term.
Hypolation.
It's called deposition. Okay? Deposition. This is snow. Snow is water vapor, and we can use dry ice. Here's an example of that. Okay? Snow is when water vapor freezes directly and goes straight to the solid. It bypasses the liquid state. So it's clouds that are full of water, but then they get hit with cold air real fast, and then it just freezes. So snow is the opposite of sublimation. So we need to know these 6 phase changes right here. So, and I went to make copies of something for you with this, but the copy machine was full. We'll work on this on Monday when everybody's here. This is my last thing, I promise. Okay? So we just said in that demo and whatever that you can control the boiling point by controlling the pressure and the temperature. Okay? So this is a graph of water at different temperatures and different pressures. And so this, along this whole line, is when water will boil as we change the temperature and as we change the pressure. So at 1 atmosphere of pressure, the normal boiling point of water is 100. But as we continue to increase the pressure, the boiling point continues to increase, until finally it gets to this point called the critical temperature, 373.99 degrees.
Fahrenheit. So
At that temperature, it doesn't matter how much pressure you put on it, it's going to turn into a gas. Okay? That's the maximum you can do. Now, the minimal amount of pressure you have to have is 217.75 atmospheres. You got to have a whole heck of a lot of pressure on it to make it stay water at this temperature. But even if you go to 374, you can put 1,000,000 atmospheres of pressure and it's still going to boil. Okay? This is the max temperature. The higher the critical temperature, the stronger the attractive forces between the substances. Now, we can do the same thing with the freezing point. Now, I'm always amazed that more of you haven't experienced this. Have any of y'all ever taken a soda out of the back of the fridge or something, and when you open it, it kind of turns into a little bit of an icy, it freezes up some? Has that ever happened? That's never happened to y'all?
occasionally, but not really.
Not normally, because your fridge isn't supposed to be below freezing.
It's happening with like water.
Oh, I don't know.
Where you take a bottle of water out and you open it and it freezes on you?
Yeah, if you
I mean,
put it in
I
the
didn't-
freezer for like a very specific amount of time, and you take it out and you smack it, it like freezes.
Yeah, I mean, I
Okay.
did it on purpose for my Gatorade when it was like middle of summer and I went to the mountain bike camp.
And so as long as it's sealed, it stays a liquid, but as soon as you, so in other words, the pressure is going to be building up in there, okay? In order for water to freeze, it has to expand. If you have pressure on it, it doesn't allow it to expand. So you can, by increasing the pressure, you can lower the freezing point of the substance, of water. Water is the only thing, one of the few things that expands when it freezes. Almost everything else contracts when it freezes, okay? So most every other substance, the line's gonna go this way. But for water, you increase the pressure, and so that's what happens when you ice skate. When you ice skate, your pressure on the skate on the water, on the ice, actually melts the ice below the skate and makes your skate go more smoothly across the ice. Okay? You increase the pressure. So it happens to me, the first time this ever happened to me was I was 22, 23 years old, single, living with 3 other guys, and I came home from church and I'd gotten a glass bottle of Coke. Okay? And I was drinking Coke back then because I was skinny. And so, glass bottle of Coke, but I was about to grade papers. I put it in the freezer because I really wanted it cold. Forgot about it. Probably fell asleep. Okay? Came down and said, oh crap, it's going to be exploded in the freezer. Open it up. Oh man, good. It didn't explode. It's still liquid. So then I opened up, popped the top, and it all turned into a Coke Icy all at once and came flying out of the top, made this huge mess, okay? I just came from church, I didn't cuss, okay? But I was very disappointed, very frustrated, okay? But because it made a mess and I'm not gonna have my nice ice cold Coke, all of those things. But then after I cleaned up the mess and it got calmed down, why did this happen? And what happened was it's under 5 atmospheres of pressure. So as long as it's under pressure, the water, the soda, couldn't freeze. But as soon as I took the top off, it went from 5 atmospheres to 1 atmosphere. There's nothing now resisting that water from freezing, and so it froze instantly, kind of like you're talking about, you tap it, it froze instantly and turned into slushy and came flying out, began to expand and filled and went flying out of the bottle. So if you keep something under pressure, it's not going to freeze. Now, almost every other substance, because it contracts, increasing the temperature causes it to, increasing the pressure causes it to freeze at a higher temperature rather than a lower temperature. Water's just unique. Thank God water's unique. This right here, what do you think the triple point is?
If it goes below that point, it's always going to immediately freeze.
No. Triple point. Here's a solid, here's a liquid, here's a gas. What's true right there?
All of them.
It's all 3 at the same time.
Ah.
At that one particular temperature and pressure, you can have ice, liquid, and steam all together at the same time.
How does that work?
Yes.
It just does. Okay? How can they be all 3 at the same time? Now, you know that you can have ice and water at the same time, right? And you know you can have water and steam or water and vapor at the same time. As we can see in the cup, we got condensation. But at this one particular temperature and pressure, 0.01 degrees Celsius, and at almost a vacuum, water can be both all 3, an ice, liquid, and a vapor at the same time.
That's funky.
Okay? And I'll let you ponder that over the weekend. Have a great day.
No, you forgot your shameless subscribe.
Oh, that's right. If you're enjoying this video, please feel free to subscribe to my channel. I need 100. I'm at 80.